Okay, well, I'm going to talk about something a little bit different, magmatic sulfides in alkaline systems. So slightly lower degree partial melts to most of the things that we've been looking at so far today. And this is work that we've been doing, looking at these sort of magmatic sulfides in alkaline systems, and in particular their association with carbonate. So work that we've been doing, Darryl Blanks is a PhD researcher at the University of Leicester. Marco Fiorentini, many of you will know, is at CET in Western Australia. So very briefly, alkaline magmatism, generally we're looking in a sort of post-subduction collisional setting during extension. And what you get is, the key thing is low degrees of partial melting. So we're talking about less than 10% partial melting. And the key thing there is that the low degree partial melts are a little bit more enriched in the incompatible components of the mantle, like volatiles. But also, you're only partially melting the sulfide in the mantle. Now, what that means is that you get a little incongruent melting, and you leave behind effectively a more MSS style restite. And you tend to mobilize copper, gold, and tellurium a little bit more. So there's a particular metallogenic flavor to these alkaline systems, and you see that gold tellurium signature in epithermals like Cripple Creek, for example, and porphyries like Skouries. But we've also seen it now down into the magmatic sulfides in the mid and lower continental crust, and that's what we'll so I'm going to be focusing on. And in particular, something that we've noticed with the sulfides in these alkaline systems is that they're associated with carbonate, fairly primary looking carbonate. So let's strip that back and go, right, okay, let's have a look at the source. Have we got sulfides and carbonate in the source? And we do. This is nothing new. There are numerous publications out there which talk about the composition of mantle xenoliths, and you often see carbonate in there. The mantle is one of a big reservoir of carbon. And these are some of our own samples from various localities around the world. And we've got sulfide associated with carbonate there. There's some tellurides there. Big pools of calcite here, again with sulfide. And we tend to see the sulfide with the carbonate. So that's quite a nice little association that we see in the mantle. But also, we start to produce these alkaline ultramafic rocks and then place them into the lower crust. These are some alkaline ultramafic pipes that are placed into the very lowermost part of the crust in the Ivrea zone in Italy. And we get these blebby sulfides, sort of centimetre scale. And around the margins, we've got calcite. And even we've got inclusions of carbonate as well. Now, normally, when us magmatic sulfide people find carbonate in our rocks, it's normally something to do with contamination or late stage alteration or something like that. And it usually is, but not always. And in this case, we're seeing calcite along the margins of the sulfide. And in this one in particular, we can see this doesn't look like secondary alteration. It's not sort of feathered and raggy or vein style. That looks like primary calcite with these beautiful cuspate boundaries around the margins of the sulfide in contact with the primary silicates, which are amphibole there. So that was interesting in the lower crust. Moving up to the mid crust, we were looking at some alkaline ultramafic rocks in Scotland, and there's a sulfide bearing one called Strong Garb. And again, we've got these blebby sulfides, pyrite and chalcopyrite here, which is reflecting that sort of copper-rich flavor, which you tend to get. There's gold and tellurium in there as well. And this calcite looks pretty primary there with sulfide, and we've got sulfides here with calcite. If you think you can see a unicorn there firing laser beams out of its eyes, then you're not the only one who spotted that. But this is okay. So these carbonates, they look primary. Do the isotopes support that? Well, then yes. So all the carbon isotopes from those samples that I've just shown you, delta 13C of about -6 to -8, which is a good mantle-like signature. The oxygen has shifted a little bit to heavier values, but you can account for that with some low temperature alteration or a little bit of rate fractionation. The main thing is they are not like xenomelts or something like that from the local country rock carbonates. Okay, so Let's go to another example here, and those of you who've tuned in hoping for a Lord of the Rings reference, it's coming. So this is probably our biggest example of one of these alkaline complexes. It's called Mordor. It's right in the centre of Australia, right in Middle Earth there. About 50 kilometres east of Alice Springs. This is a Runter block here is a beautiful exposure of mid-crustal lithologies, good for a virtual field trip on Google Earth. And you can see some amazing fold structures and this quite almost implausible mountain range with these three-sided sort of box shaped. And within that, we've got our alkaline complex made up of syenites and mafic, ultramafic alkaline rocks. Now, the reason why it's called Mordor is because if you look in Tolkien's books, that is the map of Mordor, which has this seemingly implausible three-sided box-shaped mountain range. But that inspired the survey geologists to name this area Mordor Pound. And also, if you know the story, Mordor is home of Mount Doom, the evil eye of Lord Sauron there. And Mount Doom is the highest peak in the Mordor alkaline complex has been named Mount Doom. And just to complete it, there are some hobbits looking over towards maybe working out, trying to see how they can get into Mordor. But maybe they came over here, because that's what we did. You can trek up from Trafina Gorge, a nice little campsite, and you can see over that Mordor Pound. There's Mount Doom in the middle there, looking slightly less terrifying than it does in the books. It's not easy to get in there because it's a cattle station, and therefore there's some strict biosecurity laws if you want to get in. So we didn't manage to get access, but we should have really known that, because if there's one thing anybody knows about Mordor, is that one does not simply walk into Mordor. In fact, we couldn't even drive in there, but that was okay because other people have in the past and they've drilled it. So there has been exploration in this mafic, ultramafic portion. There are some PGE reef style deposits in the Mount Doom region. Steve Barnes wrote a paper on this in 2008 in Mineralium Depositor, but we were interested in this marginal mineralization out here. A couple of drill cores that we looked at with copper and some precious metal mineralization towards the margins, and they're blebby sulfides. So the Northern Territories Geological Survey have all the core of this, so we went and spent a few days examining and sampling that, and we see these blebby sulfides again, and they're exactly like those ones from Scotland. The pyrite and chalcopyrite in sort of centimetre scale, with a little bit of millerite, not much nickel, and some PGE tellurides as well. My friends, the tellurides there. And these are centimetre scale, and they have calcite with them as well, within and around the margins of these sulfides. And we put the dilute hydrochloric acid down the cores, and the only place where it fizzed was where the sulfides were. So there's a real distinct association between carbonate and sulfide in these systems. Now the problem is these are pretty big blebby sulfides that we're seeing in these lower and middle crustal intrusions. So how did they get there? Because they should sink, especially big ones. So maybe there's something that's actually physically helping them to get up into the crust, across that moho. And the idea that bubbles can help physically transport sulfides and dense minerals in magmas has been developing over the past few years. Particularly Jim Mungal and his group have been proposing this. Also Adam Simon's group have proposed that certainly in the upper crust, their experiments show that bubbles of hydrous or saline fluids and vapors, they can stick to sulfide liquid droplets or magnetite, and effectively, if the right ratio is there, float them up. And that is one of the ideas of how El Laco formed. And we see empirical evidence of this as well, with little silicate caps on the top of sort of centimetre scale blebs in these upper crustal deposits. So it's fairly, there's some pretty good evidence that bubbles help sulfides move in the upper crust at least, but all those experiments so far have been related, mostly hydrous fluids in the upper crust. What about the lower crust? Well, the most recent paper by Yao and Mongal does state that although their experiments don't go that deep, the compound droplet dynamics should be the same. So our lower degree partial melts, they're most likely to be sulfide saturated at source because they don't melt all of the sulfide in the source. And they can be CO2 saturated as well, because the low degree partial melts, they have those higher degrees of the volatiles. Now, what we're suggesting here is that we've got sulfide and CO2 supersaturation at source, and this sort of situation can happen to move those sulfides up in these alkaline systems, at least. Might be expanded outwards, but certainly in the alkaline systems, up and physically make those sulfides buoyant and potentially cause fairly rapid upward transport. And this image, which I showed you earlier with the calcite around the sulfide, is maybe a fossilized version of that sort of compound droplet being trapped by silicates. So, as the title said, the sulfides didn't simply walk into Mordor, one doesn't, but they may have been transported up there by bubbles. And so it's a way of taking fairly big droplets and moving them a lot further up into the crust than you might expect. And they are particularly emplaced around the margins. The reef-style deposits in the middle, that's maybe a different story. But certainly these blebby marginal ones appear to have a similar sort of flavour in each of these locations that we've looked at. But we don't really see it in the upper crust. And that, why? Well, probably the reason for that is that the sulfides dissolve. As the pressure decreases and you go up, sulfur becomes more soluble, and you'll release those metals back into the crust. Now, what that does mean, though, is if you contaminate maybe with some crustal sulfur up here, then you get to maybe form an ore deposit because you prime those magnets. So what we're suggesting is that CO2 here is a little bit like the fuel boosters on a rocket launch. So it's essential to get that rocket off the ground, across the moho, into the lower and middle crust, but at some point the two sort of separate, and by the time those magmas get to the upper crust, we don't really see the evidence of it anymore. So it's only in these lower and mid-crustal deposits that we see the evidence of this process happen. So to summarize, these alkaline magmatic systems, they have a characteristic gold, copper, tellurium dominant or rich metallogenic DNA, if you like. And the key control is that low degree partial melting of probably metasomatized and enriched lithospheric mantle. Now, what that can do is we can produce magmas which are both sulfide and CO2 supersaturated. The CO2, by the way, as a supercritical fluid that's still less dense than the sulfide liquid and the silicate liquid. And as that supercritical fluid can act as a physical driver for that metal flux in the lower lithosphere. That was released in Nature Communications just last week. Daryl sent an email about that yesterday around mag sulfide. So that's the idea of the CO2 bubbles coming up. And the more general idea of this post-subduction magnetism was published last year. And if you're a little bit more interested in Mordor, we do have a paper which has been accepted and is now in press, if that's still a phrase, in these digital times, in Mineralium Depositor, which should be coming out soon. So happy to take some questions in the session, and there's some contacts if you want to get in touch. Okay, thanks very much.